So let's dig into assignment 68 today. We're going to talk more about log properties. But just a quick review for our bell work. Could you tell me, and I'd like these to be really fast, A, log base B of 1. 5, 4, 3, 2, 1. And what about log base B of negative 1? 5, 4, 3, 2, 1. That doesn't exist. I can't take the log of a negative number or 0. C, how about log base B of B to the x? 5, 4, 3, 2, 1. D, log base it's B raised to the log base B of x. There we go. Well, we know that b to the power of and log base b are inverses, and they undo each other, and so we get x here. Just like log base b of b raised to the power are inverses, and they undo each other. Okay? All right. Good. Nice. Next. How about this question? This is bell work number 2. R y equals 2 to the x minus 1 plus 3, and y equals log base 2 of x minus 3 plus 1 inverses. What a great question. So how can we know the answer to this question? Well, I think there are a bunch of different ways we could do it. We know that if we compose, let's call this f and g. If we compose f and g and f, we should get x both times. It looks a little scary to do that, though. I mean, do you really want to take all of this and plug it in there? Well, let's give it a try and see what it's like. Log base 2, x minus 3 plus 1. So all of this is that. And now we have a minus 1. Okay, well, so those cancel. And 2 raised to the power of and log base 2 are inverses of each other. Ooh, and I forgot this. Plus 3 there. So 2 raised to the power of and log base 2, those are inverses and cancel each other. So I have x minus 3 plus 3, or x. Wow, well, that wasn't so horrible, and it turns out that I got x by taking this and plugging it in there. What if I take this and plug it in there? Let's see what happens. So we're going to have log base 2 to the x minus 1 plus 3 minus 3 plus 1. Okay, so we replaced this x. So we still have that minus 3 and that plus 1. We replaced this x with all of this stuff. Okay, well, I combine like terms and those go away. And now I have log base 2 of 2 raised to the power of. They're going to be inverses and cancel each other out. So we're left with x minus 1 plus 1, or x. So yes, I can verify that these two are inverses of each other. Some people like to do this by graphing each of them and noticing that they reflect across the line y equals x. The points don't match up quite so well, so I'm a little less fond of that approach. Okay? All right, so now let's take a look at a little extension on solving. we're talking about solving log equations. And so, if I have something like log of 2x plus 1 equals log of 3x minus 5, the book would like you to use something called the one-to-one property. And the one-to-one property isn't about a function having an inverse. It's about the fact that these things are equal, and they're both the same log base. So if the terms are equal, and they're both the same log base, then the arguments must be equal as well. 2x plus 1, 3x minus 5. All right, I'll subtract 2x from both sides. I'll add 5 to both sides, and I'll get x equals 6. Remember, log equations are must checks, and we know that because log equations have a restricted domain, right? They have that big old vertical asymptote. I can't take a log of a negative number. So I'm going to have to check by plugging this back in either here or here to make sure I don't get the log of 0 or the log of a negative number. So if I plug 6 in here, 18 minus 5 is 13. Great, that's not negative, that's not 0. And if I plug in here, 2 times 6 is 12 plus 1 is also log 13. So I'm happy with that answer. All right, how about this one? Oh, wait, I meant to say that with that last problem, instead of using the one-to-one property, I would encourage you to think about, since these are both base 10, exponentiating. I know it gets us to the same place, but exponentiating is going to work in many more situations than that one-to-one property. So I would encourage you to use exponentiate. All right, so how about this one? Log base 7 squared minus 14 equals log base 7 of 5x. So what can we do here? Well, that's right, we can definitely exponentiate. 7 raised to the power of log base 7 cancels, leaving me x squared minus 14. 7 raised to the log base 7 cancels, leaving me 5x. And now it looks like one of those quadratics that we were solving in the Algebra Basics unit. So I'm going to move everything to one side because this degree is greater than 1. And I'm going to see what will happen then. Oh, factorable. X minus 7, x plus 2, and so x equals 7 or negative 2. Well, let's just confirm that that's going to work for us. If I take a 7 and plug my 7 in here, 7 squared is 49. 49 minus 14 is 35. So this is going to be log base 7 of 35. If I plug a 7 in here, 7 times 5 is 35, and I get log base 7 of 35. So that one's good. How about this? Negative 2. Negative 2 times negative 2 is positive 4. 4 minus 14 is negative 10. Yeah, I can't take the log of a negative number. It's not that this number is negative. It's that when I take the number and plug it in, I get a negative quantity there. Okay? I promise you, I write test problems all the time where the negative solution works and the positive one doesn't work. We only get one solution here for us, and that's at x equals 7. All right, how about you try this one? Log base 6 of 3x minus 4 equals log base 6 of 1 minus x. Give that one a try. Come back in a few minutes when you're done. Hey, welcome back. I hope you exponentiated. So we get 3x minus 4 equals 1 minus x. I'm going to add x to both sides and add 4 to both sides. And I'm going to get 4x equals 5, or x equals 5/4. Okay, so what happens? Well, if I plug 5/4 in here, I'm going to have 15/4 minus 16/4. That's negative 1/4. Yeah, I can't take the log of a negative number, so it's not going to work out for me. This is no solution. Okay? Okay. Next, let's talk about these properties. So I kind of want to notice something. Log of 24. When I do this on my calculator, I get 1.3802. Well, I want to take a look at some other things, like log of 6 plus log of 4, and log 24 plus log of 1, and log of 8 plus log of 3. Okay. Will you pull out your calculator and evaluate each of these? So how did that go? Did you notice something interesting here? When I add these in each case, I get 1.3802. 1.3802. 1.3802. Huh. So all of these are the same as this. I wonder if there's something I can do with that. You know, 24 seems important here because 6 times 4 is 24, and 24 times 1 is 24, and 8 times 3 is 24. Hey, do you think it works for log 2 plus log 12? Go on, try that one. I know, right? It's so freaky that that works out that way. It's the same. So I think we can say something about log mn. So mn means I'm multiplying two things together. This 24 can be the product of 1 times 24, 2 times 12, 3 times 8, 4 times 6. And look, we have 8 and 3. We have 1 and 24. We have 6 and 4. We have 2 and 12. So I think I can write this. Isn't that interesting? When I see a product, I can split that into two separate logs. Two separate logs joined with addition can be this one log where these arguments are joined with multiplication. So this is actually called the product property. Product property. Product property. Log m plus log n equals log n. When we take these and combine them to be this, we're calling that condensing. When we start here and go in this direction, we call that expanding. And there's going to be a bunch of expanding and condensing that you're going to need to do in the next week or so. So keep that skill. ACT loves these questions, by the way. Okay, so I know then that in addition to this product property, I have some others. So that's our first property. Will you please look at this? Log 12. When I do that, I get 1.0798. 18. All right. So what about not log 3 plus log 4? We already established that exists. No, actually, I want to do this other approach. I want to do log 12 minus log 1. And I want to look at log 24 minus log 2. And I want to look at log 36 minus log 3. Okay? So will you compute each of those? I know, right? 1.07918. Unless you round it along the way, which you're not supposed to do, in which case you get numbers close to these, but not exactly these. So what's happening here? When we had addition, that was multiplying these two things together. So what do you think this is all about with subtraction? I see log n minus log n. I can rewrite that how? Yeah, 1 log only, m over n. So this is my m, this is my n. 36 divided by 3, 12. 24 divided by 2, 12. 12 divided by 1, 12. And so this one's called quotient property. Here's our quotient property. Quotient property says log m minus log n equals log m over n. Here's our quotient. Okay, the last one that we have is one that we've kind of already seen. And this last one is the power property. Okay, so if I have something like log base b of b to the n. Remember, earlier in this video and in the last video, we said when we had log base b of b raised to some power, that exponential and that log would undo each other, and I'd have n. Okay? That's where we've been. But now I want to try something else. I want to think about a power property here. Log base b of b to the n. And what I want to say is, when I see that property in the at power in the presence of a log, I'm going to bring that property down in front. And what did we remember about log base b of b? That's right, we reviewed that earlier in this video, and we said that log base b of b was 1. So, yeah, bring it on down. Or, if it's down, you can push it back up. Okay, it works in either direction, this power property. You can bring the power down in the presence of a log. You know, if I just have 2 to the x, I can't bring that x down, not without some sort of log being there. Right, now that I've got the log of both sides, ooh, I can bring that x down. Okay, so in the presence of a log, I can bring down the power. If I see a power, a coefficient out in front of a log, I can kick that up. That's my power property. All right, so let's see what we can do with these properties. Okay, let's try expanding. Log base 5 of 5 over x. Well, hey, this kind of looks like that quotient property we were just talking about. I've got division here. That means I can break this up into 2 logs joined with subtraction. I see division in 1 log, I get subtraction between the 2 logs. Okay? And this goes back to that x to the 5th over x to the 3rd, that pre-algebra rule we talked about where the bases are the same and we're dividing, of x to the 5 minus 3. That's subtraction. Okay, subtraction. I'm dividing, I subtract them. I'm dividing, I subtract them. All right. I will say this isn't quite done. What's log base 5 of 5? That's right. And you won't get this right if you leave this unsimplified. So we'll take this, or negative log base 5 of x plus 1. Just flip that. All right, so that's what expanding looks like. Perhaps you could give it a try now. How about this one? Log base 5 of x squared y. Will you expand that, please? Welcome back. Did you say that was going to be log base 5 of x squared plus log base 5 of y? Well, that's a good first step, except look, you've got a power. So 2 log base 5 of x plus log base 5 of y. That's what I need to see. This would not earn you the credit. Okay? All right. Can you do then this one? Log base 7 of x, y squared. That should be very comfortable. Okay, so did you say that was going to be log base 7 of x plus log base 7 of y squared? It's a good first step, but you need to use that power rule. And so we're going to have log base 7 of x plus log base 7 of y squared. Oh, but we're bringing down that power. And so we're going to have this. Okay? That squared doesn't come down first because that squared only applies to this y. It doesn't apply to both of these. Now, if I had something else, like log base 7 of xy squared, aha, this squaring applies to both of these. In the presence of a log, I can pull that down to log base 7 xy. But wait a minute, I still have a product here. And so I can write this as 2 log base 7 of x plus 2 log base 7 of y. Please notice that this applies to both of these, right? And we know it has to because this could also be written as log base 7 of x squared y squared. And when we split this up to log base 7 of x squared plus log base 7 of y squared, we would say, oh, let's use the power rule on both of these. So we've got to have a 2 out here as well as here. Okay. Log base 2 of x squared square root y. What'd you do first here? Yeah, I split this into 2 because I saw that. I said log base 2 of x squared plus log base 2 of square root of y. Okay, again, like I've been saying since algebra basics, I'm not keen on that. I would much rather write this as y to the 1/2 power. How come? Because I know about the power rule. And the power rule says that in the presence of a log, I can bring these powers down in front. And so this one is going to be 2 log base 2 of x, and this one's going to be 1/2 log base 2 of y. Okie doke. Okie doke. Oh, how about this one? Log base 7 of 5xy. Five, 4, 3, 2, 1. Well, that's interesting. I see the product up here, log base 7 of 5 plus log base 7 of x, and this one's on the bottom, log base 7 of y. Okay, what if I had a variation on that and had x over 5y? How would that change things? Give that a try. Did you get log base 7 of x minus log base 7 of 5 plus log base 7 of y? You know, many people think about this, and so they have that. Careful though, this minus applies to both of these. Log base 7 of x minus log base 7 of 5 minus log base 7 of y. And so maybe an easier way to think about it is anything in the numerator is going to be attached with a plus. All those things in the denominator, minuses. So anything on top plus, anything on the bottom minus. And that will hold you in pretty good stead. What about this one? Log base 6 of 1 over x to the third. So, yeah, I don't want to do this as quotient. I mean, you can and you'll get to the same answer, but I would like it if you were comfortable seeing this as x to the minus 3, because then I can bring down that minus 3. Minus 3 log base 6 of x. You know, the other way where we think about this as a quotient, we're going to have log base 6 of 1 minus log base 6 of x to the third. And what can we do here? Well, the log of 1 is 0, and here's a power rule, and so minus 3 log base 6 of x. Oh, and that's the same thing. So we can get there lots of different ways. All right, and I guess I want to say, hey, think about the difference between this one, cube root of x over y, versus log base 3, cube root of x over y. Huh. Try each of these and think about, well, actually, before you try each of these, think about what you think will be the same and what will be different, and then try each of these. If you're stuck on this one, I would say it's probably worth your time to rewrite with rational exponents. And now maybe it becomes a little more apparent. This one is going to be log base 3 of x to 1/3 minus log base 3 of y to 1/3. And we can use the power rule to bring those 1/3s down. We'll have 3x minus 1/3 log base 3 of y. You could, of course, always factor out that 1/3 like this. And that makes sense to me because I could also, using exponent properties, I could just rewrite this radical as this rational exponent. In the presence of the log, I bring down the 1/3, and now I've got this quotient, so I write as two separates with subtraction. Okay? This one, on the other hand, log base 3 of x to the 1/3 minus log base 3 of y. I can use the power property here, 1/3 log base 3 of x minus log base 3 of y. Done, done. Okay, so that was expanding. You know, we were taking one tiny log and breaking it up into a bunch of smaller logs. Can we do some condensing? So, how about something gentle? ln of 2 plus ln of x. What do I need in condensing? Well, I see two logs joined with addition. That means I can turn that into one log where there's multiplication with these arguments, 2x. Okay. So if I've got 2 log base 3 of x plus 4 log base 3 of y. Again, I see a product, but wait, I see these powers. And when we go backwards, when we condense, we actually have to do the power property before the product or quotient property. Okay, so I'm going to kick that up, and I'm going to kick that up. And so I'm going to have log base 3 of x squared plus log base 3 of y to the 4th. Now, these 2 logs joined with addition can be written as 1 log with some multiplication, x squared times y to the 4th. So that's condensing. We're taking these 2 terms and condensing them into 1 log. Remember, you have to kick these up with the power rule before you apply product or quotient property. Okay? Well, let's see how you do with this one. Log x minus 2 log y minus 3 log z. Will you condense that expression? Yeah, I like that there's no power here to worry about, but I do have to kick these up. So I'm going to have log x minus log y squared minus log z to the 3rd. Remember what I said a few minutes ago. All these minuses, they're going to head to the bottom. I feel pretty comfortable writing x, y squared, z to the 3rd. Just like that. Now, you may not want to do that. I understand completely, but I'd like you to get to that place where you can. Instead, you could think about this. You could factor out a negative. Log of y squared plus log of z to the 3rd. Oops, bracket. So 2 logs joined with addition. Oh, that means I'm going to multiply these together in 1 log y squared, c to the 3rd. Hey, there's that minus out in front, and a log x. And look, 2 logs joined with subtraction. I can condense that into 1 log, where this is on top, and these are on the bottom. Ta-da! Same answer as just saying if it's got a minus, it goes on the bottom. And so I recommend that. All right. How about this one? Where'd it go? There it is. For ln z plus ln z plus 5 minus 2 ln z minus 5. All right, that should keep you thinking for a minute or two. Ready to talk? Okay. Well, let's condense these into 1. Z plus 5 with the product rule. 2 logs joined with addition can be 1 log with multiplication. I still have that 4 out in front. Now what? Well, now I want to kick these up with the power property. So I'm going to have ln of z squared plus 5z squared, oops, to the 4th, minus ln z minus 5 squared. Log connected with subtraction. So I can write 1 log z squared plus 5z to the 4th over z minus 5 to the 2nd. There it is, nice and tidy. Now, I heard some of you saying Mr. Cuckoo, a few minutes ago, you said when I go backwards, I need to take care of this first. I need to kick that up first. But that's not what you did here. So, remember, PEMDAS says parentheses exponents. So I'm taking care of what's in the bracket first, and then I'm dealing with that exponent. Okay? I mean, I think we can do it the way you want to do it, which is distribute this 4 ln z plus 4 ln z plus 5 minus 2 ln z minus 5, right? That's all that is. And then I can kick all of these up. I have ln of z to the 4th plus ln z plus 5 to the 4th minus ln z minus 5 squared. Oh, these are joined with addition, so I can have z to the 4th, z plus 5 to the 4th, and this says I can do some division. So z minus 5 to the 2nd. And since both of these are raised to the 4th, you could certainly write this as ln of z plus 5 to the 4th over z minus 5 squared. And that was my answer the way I did it. You'll get to the same place. I kind of like that there's a little flexibility here on how I approach these problems. I get the sense that you'd like one more of these. All right, so one last condensing one. 2, 3 ln of x minus ln x plus 1 minus ln x minus 1. Okay. Take a minute to tidy that up. Can't wait to see what you get. Well, I guess I could distribute that too. I think many of you are going to do that. I would kind of prefer just to kick this up and get ln x to the 3rd minus ln x plus 1 minus ln x minus 1. And the reason is because now I can take all of these and condense to one log. This is on top because it's a positive. These are on the bottom because of these negatives. Don't forget there's still a 2 out in front. This is a difference of squares. And so we could write 2 ln x to the 3rd over x squared minus 1. And now I'm going to move that power back up. ln x to the 6th over x squared minus 1 squared. And, okay, so that's condensing. Next, I'd like to do a little practice evaluation. Let's take a look at this. So I'm going to give you that log base b of 3 is 1.585. And log base b of 7 is 2.807. And then they asked me to evaluate log base 2 of 48 over 40, log base b of 48 over 49. Yeah, I haven't a clue, except I do know that I can rewrite this as log of 48 minus log of 49. And how does that help? Well, that can be broken up further. That's log of 16 times 3 minus log of 7 times 7. Ooh, I guess you could see that as 7 squared, huh? So here, those are supposed to be these. log. Yeah, let's see how it goes. Here I can break this up into log base b of 16 plus log base b of 3 minus, power rule, 2 log base b of 7. All right, well, I know log base b of 3 is this. So that can be replaced with 1.585. And this, well, there it is, log base b of 7, can be replaced with 2.807. I would I would multiply these, and I would carry out that subtraction, and that would be my answer done. Okay. I will say that in problems like this, I have seen students do this very interesting thing where they don't like that they don't know what the base is, and so they do this. They say scorpion tail b to the 1.585 equals 3. So how do I solve this for b, you say? Well, some students graph this in y1, graph this in y2, and do second calculate intersect. Other students do this. They take the log of both sides, because then in the presence of a log, they can bring down the power. 1.585 log b equals log 3. The problem, though, is I'm trying to solve for b in this situation. And if I'm trying to solve for b in this situation, I've got to divide by the 1.585, but I still have a log here, and I don't want a log. I want just b. And so then I'd have to exponentiate with power of, oh wait, this is log base. This is log, no, 10 will do. Yeah, that's a power. I find that really, really hard, but some students do that. Now, I will tell you that I did not do that in this problem, because in this problem, what I'm thinking about doing is just applying my log properties. In fact, if I told you this, my concern would be that you would pull out a calculator and then say log base 2 of 48 over 49, and you'd come up with this decimal approximation, which is in fact going to be different from mine because I've rounded to 3 places. Okay, I just want you to show off your log properties here. So remember that this is log base 2 of 16 times 3 minus log base 2 of 7 squared. This can be broken up into log base 2 of 16 plus log base 2 of 3 minus, power rule, 2 log base 2 of 7. Now we've already seen that log base 2 of 3 is 1.585 minus 2 times log base 2 of 7. There it is, 2.807. But now we've got this. Hey, isn't 16 2 to the 4th? And I can bring that 4 down in front. And what's the log base 2 of 2? That's right, we reviewed it at the beginning of this video. We said log base b of b was 1. 1 times 4 is 4. So I'm going to have 4 plus this minus this. Okay? And that's going to be 4 plus 1.585 minus 2 times 2.807. And I get negative 0.029 as my answer. Now, I do want to say something about that answer and why I expect that answer. This is less than 49 49ths. 49 49ths is 1. I know from my graph of log that this point is 1, 0. And between x equals 0 and x equals 1, all the log values are down here. So this is less than 1 over here, and therefore that's going to be equal to a negative number. Because I'm very close to this, it's only a slightly negative number. Okay. Will you use these facts, log base 2 of 3 equals 1.585, and log base 2 of 7, 2.807, to evaluate log base 2 of 12. You should not need your calculator for this. Okay, so did you think about splitting this up into log base 2 of 2, 3 times 4, which would be log base 2 of 3 plus log base 2 of 4. And then I guess we can say, well, log base 2 of 4 could actually be 2 squared. And then I could use my power property there. So what's that going to give me? Log base 2 of 3 plus 2 log base 2 of 2. What's log base 2 of 2? Uno. Log base 2 of 3 plus 2 times 1. So log base 2 of 3 plus 2. Our log base 2 of 3 was given to us 1.585 plus this 2, 3.585. Okay? Please don't evaluate this with your calculator. I'm asking you to evaluate it using the log properties and your knowledge of basic logs. Okay? Please do that. Last thing I want to talk about is something called the change of base formula. And for people with this calculator, they still needed the change of base formula. People with a newer calculator, no, your calculator will actually evaluate something like that. My calculator does not want to evaluate that. So I need something called the change of base formula. Right now our base is 2. Well, I want to rewrite this so that it has a different base, because I don't have a log base 2 button on my calculator. I have a log button and an ln button. So I'd like to rewrite this in that way. Okay, I don't know what this is equal to, but I do know I can scorpion tail it. Let's see if that helps. Base, power, answer. 2 to the question mark equals 12. Okay, well, I got to get that question mark down because that's the thing I'm solving for. And I learned in this video that there's something called the power property. But that only works in the presence of a log. So if I have log on both sides, notice this is the common log. It's not log base 2, it's just the common log. I can bring this down. I get the question mark times log 2 equals log 12. And then if I divide both sides by log 2, I get question mark alone. And this is question mark. This is equal to that. So I can say that this expression equals log 12 over log 2. And please, by all the gods that humans have ever created to worship, do not cancel these out. Do not cancel here. No, don't do it. Please, please don't do it. Yeah, that's algebra. That's really bad algebra. Don't do that. Okay. So notice though we've changed the base. This was base 2. Now these are base 10. I also, instead of taking the log of both sides, I could take the ln of both sides. And still bring down that question mark. And now I have ln of 2 times question mark, so I would divide by ln of 2. Question mark equals ln of 12 over ln of 2. See, it doesn't matter what log base I have. I could do log base 7 of 12 over log base 7 of 2. What I do know is, I'm not going to cancel those. What I do know is, I can't do any canceling here, but what I also really like is, I don't have to have log base 2 if I don't want it. I can use the change of base formula. And so more generically, we say log base b of m can be rewritten as log m over log b, or ln of m over ln of b. Yes, you could do log base 5/9 of m or log base 5/9 of b. But I've never seen someone do that except to be querulous. So these are the two most common because those are the buttons on the calculator. This is still actually, change of base still has some value, even though the new calculators are happy to do this problem for you. There's still something that we'll do in calculus that's actually made much easier if we're comfortable with the change of base formula. So I would encourage you to not throw that one away. All right, well, I look forward to seeing you next time. Have a wonderful day, and let me know if you have any questions.